Okay, so okay, so where are we? So we are yeah. So I should have, by the way, the standard way to write the Lefschetz thing is with homology, not with chromology. Okay. Okay. So what's the so what is the what is the plan? So so define cohomology, homology. In a moment, I'm going to say which is the best. What is the actual best version for? Let's say cohomology for algebraic varieties over SQ. Now, in the Lefschetz so this is called the Tal homology. Now, in the Lefschetz story that I gave, the coefficient were over the rationals, and this turns out to be impossible. It's impossible to define a cohomology theory with over the rationals that will have the properties that we need. Maybe I'll say something about it later. Why we know that it's impossible? It's a theoretic proof that it is impossible. So so instead you need to use another field, and it turns out that the field that you need to use, you choose some L prime, which is different than the characteristic of FQ, and you define something who lives over the Eladic rationals. That's what you get. Anyway, you define this notion of cohomology such that for all x, this is the dimension of this is finite, and then and if x is proper, so the notion of compactness for algebraic varieties, so for example, projective, will satisfy this. Then x f q to the d is exactly equals, no, this is not a definition. This is a highly non-trivial equation. Sum k equals 0 of the trace of Frobenius on h k tau x to the q. Okay, so that's a situation that we're in, and so, for example, let's define E. So recall that we have E prime equals y squared equals x minus x plus 1. This is not proper. This is affine. So we can try to compactify this. And we can compactify it by taking the projective variety zy squared equals x cubed minus z squared x plus z cubed. Okay, and we can look at the projective variety defined by this homogeneous equation, and this is something compact that lives inside P2, and in fact, as on the level of points, E of
Tomer, it seems like the upper part of your screen works, the pen works better there. So
okay, I'm gonna try to do this. Yeah, no, what happened is that the glass is shattered. This is why it has these issues. So we need to send it to correction. So E of FQD is just one point at infinity. Maybe I shouldn't call it the point infinity. It's the point 0, 1, 0 that you can see solve this equation. Disjoint union E prime FQD. This is something you can easily verify. And therefore, yeah, we call this E. And therefore AE D is AE prime D, which is, as we already know, 3 to the D minus lambda 1 to the D minus lambda 2 to the D plus 1. And let me just say, 1 we can also write as 1 to the D. And then we get so we get that this is now proper, so it should satisfy the same kind of, it should satisfy this formula, right? And just by looking at this, we predict that the total dimension of even homology should be 2, because we have 2 different positive eigenvalues, or it's not that the eigenvalues are positive, but positively contributing eigenvalues, and so 2 positive contributing eigenvalues and 2 negatively contributing eigenvalues, saying that the total dimension of a negative homology should be also 2. And in this case, and we remember the general principle, which is, if stated correctly, can be a theorem. I'm not going to say it precise now, but which says that if you kind of carefully lift this into the rationals, and you look at the points, so I'm going to write it this way. You take the dimension of the étale homology of X with coefficients in QL over QL. That's the same as the dimension over Q of K of the singular homology of X twiddle with the complex points with coefficients in Q. Okay, and where X twiddle is chosen correctly. I'm not gonna be precise what did that mean. And you know, and some assumptions. This is for us now a philosophical principle. In the last talk of the workshop, I'm going to say more about to what extent we know this to be true and under what assumptions and things like that. But for now, let's take it as a philosophical principle. In particular, in our case, this equation is an equation of an elliptic curve, and the points over the complex number looks like a tori. So we get that H2 is of dimension 1, H1 is of dimension 2, H0 is of dimension 1, and everything else is, and there's nothing of higher dimension. In particular, it is going to be always true that HK étale XQL equals 0 once K is bigger than 2, the dimension of X. So in particular, as you would expect if you look at the complex points, right? If you look at the variety of dimension D over the complex points, it has a real dimension 2D. So everything above it is going to be 0. And indeed, we're going to have lambda 1 and lambda 2 are going to be the eigenvalues of the Frobenius sphere. The eigenvalues of the Frobenius sphere is going to be 1, and the eigenvalue of the Frobenius sphere is going to be 3. And this is going to give us this form. Okay. Now, it's worth noting that the absolute values of, so lambda 1 and lambda 2 were the solutions of this equation, x squared 3 minus 3x plus 3, minus 3, sorry. So, so plus 3, plus 3. was the solution of this equation. And in particular, they are complex numbers. So they're complex conjugates of each other, so they have the same absolute value. And their product is -3. So therefore, their absolute value is 3 to the half. And the second statement, which one gets from the Weil conjectures, is the following thing: if X is smooth and proper, then all eigenvalues of Frobenius on HK has absolute value are algebraic integers, and for every embedding of Q bar into C, the absolute values of alpha I, such an eigenvalue, is Q to the K divided by 2. That is always the case. Okay, so we get this phenomena that not only so what do we learn? In the smooth and proper case, and soon I'm going to say something in the more general case, we get that those alphas and betas, right? They are always algebraic integers whose square, such the square of their absolute complex norm for every embedding. Note that generally for most algebraic integers, they can have different norms in different complex embeddings. Our numbers all have the same norm for all complex embeddings. This is a property of a number, of an algebraic integer. It doesn't have to be satisfied, right? So, for example, consider the number 1 plus square root of 1 plus square root third square root of 2, right? That this is a number whose different complex. Maybe do a simpler example. 1 plus square root of 2. Its other complex embedding is 1 minus square root of 2. It's not true that those absolute values are the same, right? So it's generally not true for an algebraic number that it has a well-defined norm as a complex number. All of the algebraic numbers that we're going to see have this property as eigenvalues of Frobenius. Furthermore, those norms are always going to be, if you square them, an integer power of the size of the underlying field. Okay, so that is going to be true always. And what's going to happen in the smooth and proper case, which is the pure case, is that those absolute values are going to correspond exactly to the cohomological degree in which they appear. So this last statement is only going to be true under assumption of smooth and proper, not true in general. Okay, so and this second statement, that's the one that we're going to spend today and tomorrow and the day and Wednesday proving.
Okay. So question.
Yes.
Only if you want to address it, but perhaps you can say just a few words about the distinction between the properness and smoothness in affecting the last thing you said about the eigenvalues.
I'll get to that. I think I'm going to say something about it very soon. Okay, so so now the question is, how are we going to prove this? So I gave you a very, very nice description in the smooth and proper case of what we expect to happen. And I told you that in the non-smooth or non-proper case, you don't get this. So you do get those absolute values are those numbers are those nicely behaved numbers, but you don't get that they really live in the right homological dimension degree always. But the one important thing to say is that even if you're interested only in the case of smooth and proper, it will be very important for us to not assume those assumptions, because the proof that we are going to use is going to use the way we're going to prove this is we're going to change. We're going to do reduction steps that change the algebraic variety we're working on, and as a result, we are going to have to, even if we start with something smooth and proper, we're going to have to move through things which are not smooth and proper. Okay, so now the thing that I want to do is I want to kind of try to say, how do we say such a thing without the assumption of smooth and proper, and hopefully we'll slowly we'll get to where we want. Okay, so the first thing is that it turns out that it's not true it is not the correct thing to take chromology when we are working with a non-proper scheme. So we need to replace it with the notion of cohomology with compact support. So it's becoming worse and worse. Okay. Okay. So the Grothendieck-Lefschetz formula, what it tells us is that x f q to the d actually is the sum of I minus 1 to the I, and then put the trace of Frobenius on the cohomology with compact support, the Aladic cohomology with compact support. Now, none of those things are defined, but this is the analog of cohomology with compact support in the topological realm. Okay? So really the thing that we're looking at are eigenvalues on the cohomology of compact support. When your object is, in topology, when your object is compact, which is correspond to being proper in algebraic geometry, then those two things are the same. Okay, that's the first. Now, how are we going to? So really, the statements are going to be with regard to this, with regard to those groups, rather than the groups given by the usual cohomology. Now, the second statement that we're going to want to make, is how are we going to attack this? So the way we're going to attack it is by trying to induct on the collection of varieties in which we know the statement. And we need to describe a statement which we expect to be true not only in the smooth and proper case. So our induction can go through varieties which are not necessarily smooth or proper or both. And there's essentially going to be two essential kinds of induction steps. So step number one maneuver that we can do is that if we have a variety and we have an open sub variety and we have a closed complement, then the number of points for example, here is just the sum. Well, this is just the union, disjoint union. So that is a maneuver.
The x in the parentheses.
Oh, sorry?
The x's in the parentheses, they don't need to be there, right?
Oh, yes, of course not. Thank you. So this is one very important maneuver, the ability to decompose a variety into an open part and a closed part. This is something that doesn't destroy smoothness, but does in general destroys properness. You made a hole, you punctured your thing, which is close. So this is.
Can't Z be non-smooth?
It could be singular.
I'm sorry.
If you start with X, which is smooth, I think Z can be.
Of course. Yes. What I was trying to say that if this always essentially destroy properness. It tends to be something that destroys properness. You're right that of course you can, if X is smooth, you might remove out of it something which is non-smooth. That's true. But essentially, as long as at the moment that it's connected, if it's proper and you kind of remove something, it's going to always destroy the properness. But yes, you're right. It's both things are not. Now, those maneuvers allow you to kind of choose some sub scheme that you prefer to work with, and that's fine. But this doesn't really allow you to do the main thing that you want to do, which is decrease the dimension, and making the dimension lower. So what do you do? Well, there's another maneuver that you want to do, which is if you have a map from X to Y, which is nice enough map of varieties, you want to think about Y as having a lower dimension than X, then you want to say that somehow working over X is the same as working over Y and over all fibers of F. When you're looking at it as a counting problem, you can just write down the following thing: the number of points is the same as the sum for all Y in FQD of the fiber. Right? This is what you get. So you want to somehow you want this to be something that you that you can do, but there's nothing in the way that there's nothing in the way that the chromology described is written that allows you to do this. So what do you do instead? Well, the chromology, étale chromology with compact support is actually defined as the following thing. You have you look at shifts over X, certain analytic shifts, and there's a functor F lower shriek from here to here point. which is QL vector spaces. And this is a functor this is a functor for complexes of sheaves. And if you take the trivial sheaf on X, constant sheaf, and take F lower shriek of it, and then take pi minus k of this, this is in fact the definition of the étale cohomology with compact support. But this F lower shriek is actually defined for the right kind of sheaves for every map. So the idea is make claim for arbitrary F lower shriek for X F to Y, and thus reduce to okay, so then what do you do? So first we're going to make a claim. I'm going to say what it is for an F lower shriek, a general F lower shriek, and then by decomposing your variety and decomposing the map and do it again and again and again, this more general statement, it's enough to prove it only for X equals A1, Y equals a point. So we're going to prove a much more general statement for an arbitrary sheaf on some notion of a sheaf on our varieties. But we are going to prove this statement. So we're doing the following trade-off. Instead of being required to prove a specific statement about the eigenvalues of the cohomology only for maps which are smooth and proper, but for all such maps, we all varieties which are smooth and proper, but all such varieties, we are first going to make a much more general statement that has to do with a generalization of it, which has to do with arbitrary sheaves and arbitrary maps of varieties. But this extra flexibility will allow us to only prove this general this statement after a bunch of reductions only for the case of A1 and not in any other case. And that's and for that we're going to have a special tool of proving it. Okay, so that's the statement. Okay, so in order to make this statement precise, what do I need to do? Well, I need to tell you how to think about those size of eigenvalues for general sheaves and what kind of sheaves am I looking at. And okay, so there's a bunch of things to do here. The problem is that the screen really becomes more and more terrible as time passes. Okay, so so let's go back to the original formula, right? So what we had is X is of F Q to the D is the sum of the Frobenius to the D applied on the I cohomology, on the K cohomology. QL, and the statement was about those eigenvalues. Okay, this was this was essentially the statement. So what do I want to know? I want to talk about eigenvalues of now this thing, as we said, is just F lower Schrick of the constant sheaf. This entire information for all i's together, put together. So so what do I want to do? I want to somehow give for so I want to have a notion of a sheaf on my X such that I can measure the size of eigenvalues or Frobenius on it. This is one. And two, I want to say that F lower Schrick behaves well with respect to these measurements of eigenvalues. Okay. So, okay. So what do I need? So what do I need to do? So I'm going to give a definition. It's going to appear later again, but a Weil aladic sheaf on X is the following thing. I'm going to base change X to the algebraic closure. This is my geometric guy, my topological guy. And I'm going to take aladic sheaves on this. We're not going to give a formal description of this, but the idea is that it's something that looks like constructible sheaf. So it's some notion of a sheaf that that on an open strata looks like a local system, and then on some closed strata, locally you can decompose into locally closed strata, such that on each of those strata it looks like a local system. And I'm actually looking at complexes of such things. And what I'm interested in are this thing has a Frobenius action, and my notion of a Weil sheaf is going to be as a sheaf together with the information of an isomorphism to what happened when I pull this sheaf via Frobenius. So this is kind of like a descent data from the, it's an equivariant sheaf with respect to the action of Frobenius, okay? And those kind of sheaves I'm going to define.
So just to be clear, the Frobenius here acts on the category. So
yes.
Like it takes a sheaf to another sheaf. So we wanted the identification of like acting on the sheaf with the sheaf.
Exactly. Now, if X is a point in FQ to the D, right? Then now note that if you gave me an isomorphism with the Frobenius acting, I also get an immediate isomorphism with defined with the Frobenius of the I get right. I can apply the Frobenius upper star to this isomorphism because it's actually the category. What?
I suggest you denote the isomorphism of F and Frobenius upper star F by phi.
Okay, thank you. So so I can pull back this guy. Okay, and now I have a canonical isomorphism to the Frobenius applied twice. Okay. So now let's say that I have some point X in FQ to the D, right? So I can look at the stock of F restricted to X, and if I'm thinking about X as if I'm thinking about X as a variety over the algebraic closure, since I'm looking at spec FQ to the D, and I'm thinking about what is it when I base change it to the algebraic closure, right? Well, this looks like there's D different points. This is what this thing is. It's D different points. And I map it to X bar, and I have my Frobenius action, and the Frobenius just move them cyclically. Because the Frobenius is the generator of the absolute Galois group of FQD. So, it looks like just the inclusion of an orbit. And now, what I've been given once I pull back my sheaf, right, to here. So so on one hand, an étale sheaf on this looks like just a vector space with an action of the Frobenius, but on the other hand, I have just identified the pullback of, if I take the pullback of this sheaf to here, I have just chosen an identification. If I take the composition of those things D times of this vector space with itself. So really, I get a canonical map that is kind of a Frobenius to the D from the sheaf at X, the stock at X to itself. And
it's more like phi to the D.
Yeah, that's true. It's more like psi. It's kind of twisted form of psi to the D. So this is a map of vector spaces, finite dimensional vector spaces, and I can ask about its eigenvalue. I can ask about the collection of eigenvalues, and I can look at the maximum of alpha eigenvalue of psi to the D of the absolute value of alpha, right? Now recall, I want to think about this as q to the some integer divided by 2. So what I can do, I can take the logarithm, I can take the square, and it's going to be q to the I, and then I'm going to take the logarithm divided by the logarithm of q, right? And this is going to be my I that I'm looking at. And lastly, there's a certain normalization here. If I'm thinking about I want the eigenvalues of this psi, but I took the psi to the D, so really I want to divide by D as well. So this is the weight at the point X of F, and then I can take the maximum over X in X of the weight of F. Okay, and the statement is going to be that F lower Schrick. Okay, so now let's
can I ask?
Yeah.
The small f is the sheaf f, right? It's not the function.
Yeah, it's a sheaf.
Like the wx is of the sheaf, right?
Yes, exactly. Okay, so this gives me a notion of a weight of a sheaf. Okay, and note that specifically, if I take an F lower Schrick of QL, okay, then and I take the minus K homotopy group of this, then what I want to say that if F is smooth and proper, then the weight of this is I, essentially. That's the K. That's what I wanted. That is and F is the map from X to the point. Okay. So what's going to be the general statement that I'm going to want to make? So the general statement is going to be that for all maps. Now for QL, if F is my trivial, if F is the trivial sheaf, right? Then note that this thing is 0. because the eigenvalues are all 1, so I take the logarithm, so it's 0. So W of the trivial sheaf is 0, okay? So really, the general statement is just going to be that the minus K homotopic group of F lower Schrick can at most increase my weight by K. So I'm going to think about this K as K plus 0. So what is the statement? So what is the Ling's theorem? Okay, I have a map for X from X to Y. So first of all, I have a category of Weil. I have Weil sheaves for X and a category of Weil sheaves for Y, and I have an F lower Schrick between them. That's the situation that I'm in, and the statement is that if F is a sheaf YXQL, then pi minus K F lower Schrick F. So this is going to be in the heart. This is going to be an actual sheaf. And I'm going to take W of this thing smaller than the weight of F plus K. Okay, that's going to be the general statement.
Tamar,
Yeah.
if you want to prove this thing by some kind of induction, I guess you want to have a statement when you start with F, which is not necessarily in the heart as well, right?
Yes, you're right. So okay. Okay. So the statement doesn't really. Okay. So I need to. Okay. So the statement doesn't really require the heart. The reason that I assume that it's in the heart because the way that I define the weights, it required this thing to be a vector space. But actually, once we're going to have, I had to do some kind of a trade-off in this talk between giving very formal definitions that requires a little bit of technology and being slightly imprecise. So we can define this W for a complex essentially as easily, and then the statement just going to be as general as you want it to be. It's not going to matter very much, this distinction, because when you're trying to describe F lower Schrick of a complex, it's dependent in a very tractable way on its F lower Schrick of its homologies. So really,
okay, so just to be sure, you can say that the weight of a complex of sheaves is lower equal than W if the kth cohomology sheaf has weight lower equal than W plus K, and then just you can say that lower Schrick preserves this condition of being of weight lower equal W.
That would be the best way to say it. Yes, that would definitely be the best way to say it. So okay, so so this yeah. So maybe I'll say what Lior said. Yeah. So another way to say it that you can say that F is of negative weight. Okay, so this way you can define for a complex of sheaves WK to be the maximum of the weight of pi K of the complex plus K, and then if you define it this way, the statement is just that F lower Schrick of K is smaller or equal. Okay, that's a very nice way to say it. I want to conclude in two remarks about this. So okay, so the idea is to, again, this was kind of a preview to the proof. So we're going to carefully define those Weil sheaves, and we're going to carefully define this weights, and then we carefully going to prove that this that they have those functors lower Schrick exists, and other functors that we're going to use for the same goal, and we're going to show some basic nice behavior of those functors, and once we'll have all of this, it will allow us to prove that we have a very general statement about a map from X to Y, and then we will be able to decompose those maps using open and closed strata, and then you have a map of codimension 7, so you divide it into 7 maps of codimension 1, and then you do it, and once again you decompose it because maybe the maps are not nice enough, and again and again and again and again, until at the end it will be enough to just prove this statement for a map from A1 to the point. So there's 2 last things that I want to say. One is, how do you prove the map from A1 to the point? And the second one is, there seems to be an inequality here. And the Weil conjecture, as I said them about smooth and proper, seems to be about an equality. They were not upper bounds about the weights. They were equations. They told us exactly what the weight that we expect at a given cohomology. So those are 2 last things that I want to say about. One is, how do we get from that? So, okay, so let me start with how do we get from this statement, the statement that we want? So how do we bound the weight from the other side? Well, if X is smooth and proper, WXQL is going to have a Poincaré duality. Okay, and it's going to have a Poincaré duality, so it means that for every sheaf, we will be able to talk about its dual sheaf, and this is going to take essentially up to some shift that doesn't really matter right now, weight k to weight minus k, and so in the smooth and proper case, you can use the Poincaré dual to bound the weight from the other side, and you're going to get a precise equation. You're going to get the exact number that you need, because it's going to be smaller than equal and bigger than equal than the thing that you want. So that's one remark. And the other remark is, well, how are we going to prove it for the case of A1? So now we're in a very, very specific situation. We have a Weil sheaf on A1, and we want to prove the statement for this category and this category only. So we don't have any algebraic varieties other than A1 anymore. And the point is going to be that this category admits an endofunctor called the Fourier transform. So given a Weil sheaf, we can construct another Weil sheaf called the Fourier transform of it. And the statement for the Weil sheaves for A1 is going, so T is going to behave, I don't have time to say more, behave as a Fourier transform. In particular, it is size preserving in some precise sense. And this size is going to be this related to W, which would allow us to control it. So I wanted to say more about this, but I don't have the time. So instead, I'm just going to say, as a kind of roadmap, that we have 3 tasks essentially ahead of us. So the one thing is that we need to develop the theoretical structure. We need to talk about what are those Weil sheaves, and we need to give we need to give a more careful definition of those weights, and we need to give a more careful definitions of those F lower Schricks and other related functors. So that's step 1. Step 2, we're going to need to use all of these categorical mechanism to reduce to the case of A1. We need to show that we can really take our algebraic varieties and decompose them in this way. So the only thing that we need to prove is for A1. And then for A1 specifically, we are going to define the Fourier transform, and it's going to be the statement that we need is going to be a quite easy consequence of the existence of this Fourier transform. And it's very, very basic properties. That's it. I'm going to stop here.